Now we'll work through some sample problems from Moodle Quiz 1, starting with number 1. And number 1 tells you the average rate of reaction for reactant A is 0.649 molarities per second. What is the rate of reaction for B? And we're given this balanced equation. And so we'll use stoichiometry to figure this out. 0.649 molarity per second of A times, draw a line, bring down moles of A, and we'll go to moles of B. 3 moles of A equals 4 moles of B, and so this will leave us with 0.8653, and you're going to be left with molarity per second of B, and this would be letter E. Okay, still under average rate of reaction, and let's look at number 3. We're given 0.52 molarities per second of water, and we're asked what is the rate of reaction for oxygen, given this balanced equation. So 0.52 molarity per second of water times, draw a line, bring down moles of water, and we'll go to moles of oxygen. It is a 2-to-1 ratio. And so when we do this math, we get 0.26, and you're going to have molarity per second of oxygen, which is letter D. In number 10, how are the rates of reaction related for this chemical reaction? And he has told you that it's unbalanced. So first we need to balance the equation. So let's write C2H2 plus O2 yields CO2 plus H2O. There are 2 carbons on the left and only 1 on the right, so we need a 2 here. 2 hydrogens, 2 hydrogens, 2 oxygen. 2 times 2 is 4, plus 1 is 5. So if I had 5 over 2, 5 divided by 2 times 2 is equal to 5, which balances my oxygens. If you had balanced the equation to get a 2, 5, 4, 2 ratio, you would actually want to reduce it so that you have a coefficient of 1 in front of C2H2. Now, remember that these 2 are the reactants, so they're disappearing. So I would write a negative change in the concentration of C2H2. And remember, it's negative 1 over 1. This is all over the change in time. It's 1 over 1 because this has a coefficient of 1. This is equal to a negative, and we're going to actually invert this fraction. So 2 over 5, and that's going to be change in concentration of oxygen over the change in time, equals, and now we have positive values because these are our products, which means they're being formed. So we have a positive, inverse of this coefficient is 1 over 2, and that's going to be change in the concentration of CO2 over the change in time, and that's going to be equal to a positive 1 over 1 change in the concentration of H2O over a change in time. And so when we look at the answers, we come to letter negative, negative, positive, positive, 1 over 1, 2 over 5, 1 over 2, 1 over 1. So letter D is going to be the correct answer for number 10. Number 13, find the reaction that corresponds to this relationship. And so notice that we have these 2 values are the positives and this one's the negative. Remember, the negative represents my reactants, is what's disappearing. So NH3 is the reactant, yields, and both of those are positive, so they're both forming, so they are both my products. And now I just need the coefficients of these, which I can find in the denominator. This is a 1 to 3 to 2 ratio, so there's 2 in front of ammonia, 3 in front of hydrogen, and a 1 in front of nitrogen. And so this would be the correct answer, and that is letter C. Now we'll make our way through the category labeled reaction orders. And so number 1, Determine the rate law for the elementary reaction. Because it's an elementary reaction, we can use the stoichiometry in order to determine the rate law. So this will be the rate is equal to the rate constant times A plus concentration of B, times the concentration of B. And because these have a 1 and 1 stoichiometry, they're both raised to the first order. And so the answer to this would be letter D. So unlike number 1, this is telling you that the rate law is for the complex reaction A plus B yields C. And because it's a complex reaction, it actually has several, or at least more than one, elementary step that makes it up. And so we actually cannot use the stoichiometry to figure this out. The orders of A and B, we'd actually have to have experimental data, and so the answer to number 2 is you cannot determine this without experimental data. Number 3, the rate law for this reaction is found from experimental data to be rate is equal to the constant times NO2 squared. If this is the rate law, then these must be the reactants in the slow step. And so the slow step would either be NO2 yields as my reactants, 2 NO2, or you might see the 2 NO2s separate from each other. But it's important to know that this must be the slow step because the rate law is always based off the slow step when you're given several steps in the mechanism. And so when we look at our answer choices, that says fast, fast, slow. However, these are the two reactants in the given equation. Or no, they're not even the reactants in the given equation. Here, slow, NO2 plus NO2, C is going to be the correct answer. But just to check, see fast, fast, slow, NO2 plus just NO is why E is not the correct answer. In number 5, a complex reaction consists of these two elementary reactions, and the rate law is determined to be this. So remember, the rate law is based on the slow step in an elementary set of elementary reactions. So that means that A and B, as my reactants, are going to be the slow step. And so this being the slow step, and this is the fast step. So what that means is if this is slow and this is fast, then the rate of K2 is much greater than the rate of K1. And so we would choose E for this answer. Number 7, and this is going to be actually quite a challenging problem. This complex reaction, A plus B yields C with the K1 constant, has a rate constant with units of molarity to the negative, moles to the -1 times liter times seconds to the -1. The order of the reaction for reactant B is 1. What is the order for reactant A? So first of all, when we write the equation, rate equals K1 times A to the, I don't know what N is, but B is raised to the first order. The units for rate are molarity per seconds equals, they've told us that the rate constant K, see how it's molarity in the denominator and liter in the numerator? That means that you're dealing with 1 over, and the molarity is in the denominator, times seconds, which is also in the denominator. So that is what K is. We don't know the molarity, the order of A, but we do know it's in a unit of molarity. And then we know that B is in a unit of molarity as well, and it's raised to the first power, and so it's just M. So we want to figure out what is N. So first of all, notice that this molarity and this molarity cancel each other out. Now, I'm going to go ahead and move this 1 over seconds to the other side. So I'm going to multiply both sides of the equations by seconds. So that's going to cancel out the seconds. This cancels out seconds over here. So what do I have left? Molarity is equal to molarity to the nth power. So what could N possibly be in order to make this a true statement? m raised to the power of blank is equal to m. And so n is going to have to be equal to 1 because molarity raised to the first power is going to just equal molarity. And so the order of A is 1, which is letter E. Now look under the heading Units for the Rate Constant, and we'll work out number 1. What are the units for the rate constant K in the following rate law? And notice that you have a P in the parentheses. That means we're dealing in pressure. And so we're going to have atmospheres instead of molarity. So the rate is equal to K times the pressure of hydrogen raised to the first power times the pressure of bromine raised to the first power. The rate is going to be atmospheres per seconds equals, we don't know what K is. This pressure is in atmospheres raised to the first power times atmospheres also raised to the first power. And so now it's going to be, you can simplify this and say you have atmospheres per seconds equals K times atmospheres squared. And I want to get K isolated, so I'll multiply both sides by 1 over atmosphere squared. This will cancel, and so K is going to equal, notice that this atmosphere cancels with one of these two, and I'm left with 1 over atmospheres seconds, which is the same thing as saying atmospheres to the -1 times seconds to the -1. And so the correct answer is going to be letter B. What are units for the rate constant K in number 3 in the rate law that we're given? So rate equals K times hydrogen raised to the second order times bromine raised to the 1/2 order. So rate is molarity per second equals, we don't know what K is, this is going to be molarity squared times molarity to the 1/2 power. Remember that when you multiply m squared times m to the 1/2, you can actually add together these two to one another. And so we'll have molarity per second is equal to K times the molarity to the, and this would be 4 over 2, so this will be 5 over 2 power. Now I'm going to go ahead and multiply both sides by 1 over m to the 5 over 2 power. That'll cause these to cancel. And now I just need to simplify here. And now we're going to be subtracting. And so 2 over 2 is going to be subtracting with 5 over 2. And I'm going to be left with K is equal to 1 over the molarity to the 3 over 2 power times seconds. Or or molarity to the -3 over 2 times seconds to the -1 are my two options. And so that's going to give me letter D, which, recall, molarity to the -3 over 2 would be the same as moles to the -3 over 2 times liters to the +3 over 2. So D is going to be the correct answer.